Good morning, good evening, or good afternoon, whichever is applicable to you. Welcome to our first virtual lecture. Today, I want to start chapter 1, part A. There will be part P for chapter 1. Chapter 1, part A will cover section 1.1 through section 1.5, and part P will start from chapter 1, section 6.1 to section 6.1 all the way to section 1.9. Allow me to share my screen and show you the lecture slide. I have the PowerPoint slides on my left side, and this will be my whiteboard on the right side of your screen. This is the required text. If you haven't purchased, please make an effort of getting the required text. Test chemistry, molecular approach by through 6th edition. Chapter 1 is on matter measurement and problem solving. I know the terms, they are not new to you. You may have covered in introduction to chemistry if you took the course before. However, I want to just quickly break down the terms used in our title for chapter 1, matter measurement and problem solving. By end of chapter 1, you should be able to define what matter is, measurement, and be well-rounded in problem solving. Well, matter is defined as anything that has mass and occupies space or has a volume. You can also break down this. This mass is simply amount of matter in substance. All right. It's just to define the terms. There'll be some terms, vocabulary you need to be well-rounded. You should be able to define those terms. For example, what matter is, and volume is basically the amount of volume occupied or the amount of space occupied by matter. Now, what is measurement? Measurement consists of two things, all right? Here matter consists of n number and a unit attached to it. This what constitute what we call a measurement in chemistry. Without a number, we choose the magnitude and the unit. So for that, use, for example, here in length, we can talk about the distance from here to Miami, 358. If we don't include the units, the number will just be a meaningless number. So all measurement must include a unit attached to it. Okay, this will be very critical in the lab when you record the data, collect the data. You need to include the units. They will expect you, your instructors will expect you to record your data, including the units. Towards the end, we will look at the problem solving, and this is basically the dimensional analysis. And it is just a powerful way of solving problem in chemistry. Remember the factor label method in intro. Sometimes we call it factor label or dimensional analysis, which is a powerful way of solving problems in chemistry. Let's just see what I have in part A. This is part A, the roadmap for part A. We will look at atoms and molecules in section 1.1, the scientific method. In 1.2, as the way scientists conduct or do science. Classification of matter in 1.3, that is classifying matter as solid, liquid, or gas, and also breaking down to mixtures, homogeneous, heterogeneous, and so forth. In section 1.4, we look at the physical and chemical changes, physical and chemical properties, and finally, before we wrap up part A, we will look at the energy, which is fundamental part of physical and chemical chain, physical and chemical chain. So let's see if you are asked, what do you think is the most important idea in all human knowledge? All right. As a chemist, probably the answer will be the properties of matter are determined by the properties of the molecules and atoms which make them, right? You may have different answers, but that's just an opening remark in the text. And also, I'm just going to use it as an icebreaker for chapter 1, part A in our lecture. So let's see, what are atoms and molecules? I know sometimes some folks confuse or they use interchangeably molecules, atoms, substances, and compounds without drawing a parallel between those terms. I'm going to divide the two you see there, atoms or atom. Let's just go with a single atom. Just is it is a Greek term derived from atomos, which means small, indivisible, indestructible part of matter, all right? It is the simplest form of matter that is the smallest you can think of. Molecule, in other words, when two or more atoms could be of the same element or different elements, they form chemical bonds, and what we end up is a simple form we call molecule. And strictly talking about the molecular compounds. So the term here, atoms, is derived from the word Greek atomos, which means small, indivisible, indestructible part of matter. The properties of, let's say, for example, water molecule is determined by how water behaves. The properties of sugar molecules determine how sugar behaves, all right? We will see in chapter 2 in details part of the molecule and or rather part of the atom, subatomic particles, and so forth. In order to understand matter, which we define at a molecular level, we need to understand how atoms behave. So atoms are submicroscopic particles that constitute the fundamental building blocks of any matter you can think of. So these are the smallest, indivisible, indestructible. Moving forward, when you see the bolded terms, could it be in the text, please make your own notes. You may see it in an exam. You may be required to define those terms. Now, free atoms are rare in nature. Instead, they bind together in specific geometric arrangement to form molecules. For example, H2O, the H2O water molecule is made up of two hydrogens and one oxygen, which are chemically bonded. We call this molecule. And recall when we use the word molecules, we refer to those compounds made up of only non-metals. You should be able to recognize coming from, let's say, intro. If you took intro not too long ago, you should be able to break the periodic table into non-metals, metalloids, and metals. And when we say molecules, we refer strictly to those compounds made up of non metal plus non-metal, two non-metals. But for a metal and a non-metal, we call this ionic compound. We're gonna talk about this later on, because this is a metal and this is a non-metal on the periodic table. Just to draw a parallel between the word molecule and formula unit, all right? Or for ionic compound, we call formula unit, which is the simplest form of ionic compound. But for non-metals, we use this term, the word molecule. Here, we use different color coding for portraying molecules or to illustrate molecules. Remember, in molecular modeling, if you had to build molecules, you use red for oxygen, white for hydrogen, and this represent water molecule consisting of two hydrogen atoms and one oxygen atom. In chapter 8, we'll see more, or we'll see in details molecular models and more how molecules are built with different spheres having different colors. Now, the point here is, what is the difference between atom and a molecule? This is a molecule consisting of three atoms, two hydrogens and one oxygen atom, representing the water molecule. In each of the molecules for water, two hydrogens atoms and an oxygen atom are held together by a chemical bond. Down the line, we're going to talk about different types of chemical bonds. In chemical bonding one, we will talk about the covalent, the coordinate covalent, ionic, all right, and metallic bonding. For now, just understand that a chemical bond holds atoms together in a molecule. So let's see if we want to understand the substance around us, we must understand the atoms and molecules that compose those molecules. That is the central core of chemistry. And basically, chemistry is the science that seeks to understand the behavior of matter by studying the behavior. Sometimes you may see this chemistry. All right, let me just define this. Chemistry can also be defined as study of matter and its transformation. This also constitute, or you can loosely define chemistry as the study of matter and its transformation. Transformation, melting, all right, those are the terms or the transformation we will see later on, transformation of matter, or you can simply define chemistry as science that seeks to understand the behavior of matter by studying the behavior of atoms and molecules. For example, here you see this is diamond, this is the graphite in a pencil, and you look at the molecular level, you see that graphite atoms are patterned in the sense that there is a thin or there is a layer of atoms of graphite, but in diamond, even though all of them, they are made up of carbon atoms, all right? Small difference in atoms and molecules can result in light difference in substances that combustion. So if you look at these two, the way they are arranged affect the chemical or physical properties, even though they have the same type of atoms. Graphite and diamonds, they are made up of carbon atoms, right? Graphite, diamond are both made up of carbon. You know, the element on the periodic table. It's just illustrate the difference between them. Now, let's see chapter 1, section 1.2, the scientific approach is simply the way scientists do study science. There is a systematic way of studying science we call scientific method, and the approach to that is based on observation and experiment. You observe, and then you do the experiment. Certainly, you are familiar with experiment. I know you may be taking lab section for this course. Every day you have to go on campus and collect the data or perform the experiment. So initially, before the scientific method was devised, people didn't have a systematic way of doing science. So scientific method is a process for understanding the nature by observing and the behavior of nature by conducting experiments to test ideas. There are some terms associated with a scientific method, all right, which I expect you to make your own notes and understand what they mean. Observation is simply the data you collect, always data, where's your data? In the lab, you collect the data by making the observation. It could be recording the mass of your reagent, volume of your reagent, the temperature of the reaction, and so forth. All those constitute what we call the data, and they are collected through observation. Data are simply description about the characteristics or behavior of nature. An Italian by the name Antonio Lavoisier, he was an Italian, noticed that there was no change in total mass of material within the container during the combustion. And what he did was, he was burning or taking a substance, burn it in a closed container, weighing it before and weighing after. There was no mass loss. In other words, is credited for the law of mass conservation, which states that matter cannot be created or destroyed in a chemical reaction. It's only that the atoms are being rearranged. So remember, what he did was just only performing experiment by combusting substances, weighing them before and after, and the observation led to what we call hypothesis. And what is hypothesis? Hypothesis is, some folks define it as an educated guess, all right? But how do we define that? Hypothesis is just a tentative proposal. If you look at the definition, you need to understand hypothesis is a tentative proposal or interpretation or explanation of observation. For example, Antoine explained that his observation on combustion by hypothesizing that when substances burn, it combines with a component of air, component of air. Sometimes hypothesis will be defined as a statement which has not been proven right or proven wrong. So you just come up with a statement and then you perform the experiment to see if it is false or if it is true. One characteristic of a hypothesis is that it's falsifiable. That means the result of an experiment may support an hypothesis or may prove it wrong. It can go either way. Remember what I said, sometimes hypothesis could be a statement which has not been proven wrong or proven right. That's what's meant by falsifiable. Scientific law is a statement, it's a brief statement that summarizes past observation and predict a future one. All right, scientific law, for example, law of mass conservation in a chemical reaction, matter is neither created or destroyed. It indicates that past observation and can predict the future as well. We need to be able to differentiate between those two. Scientific law, hypotheses, all right? Remember when we talk about the scientific law or strictly law here, it's different from the government laws. Okay? It's not that you will get a ticket if you break them, but you will lose points if you don't know how to define what scientific laws stand for. Now, theory, there was, remember when we go back the experiment, what you should know what experiments are hypotheses, scientific law, and now theory is one of the well-established, all right? Hypotheses may also form the basis for scientific theory. A scientific theory summarizes, okay, known observation, and it can also predict what we know. Scientific theory is a model, such as the Dalton's atomic theory. It explains, all right, it tries to explain merely what nature does and why, all right? For example, in the law of mass conservation, Antonio could not explain why, but Dalton had to explain using his atomic theory, which we will cover later on in chapter 2. Theories are validated by experiments. So how will you know that a theory is valid? Is by performing the experiment. There is a summary or the flowchart for all these what we are just talking about, general characteristic of behavior for nature for theory. But what I wanted to say is the basis for a theory. It explains past observation and predict the future. For example, Dalton's atomic theory is a model which explains Dalton's try to explain the law of mass conservation based on his assumption of what actually the atom is. In summary, this is the flowchart of our scientific theory that you make the observation, and sometimes once you collect the data, you have the hypothesis which can be promoted to a theory if it summarizes or if experiments support the hypothesis can be promoted to theory. If not, then more experiment can be formed by amending it if it confirms some hypothesis, or it can become a law. I will not ask you in the exam to reproduce the diagram you see on the PowerPoint slide, but the point here is please make your own notes. You should be able to explain what hypothesis is, scientific law, the theory, experiment, and observation, and so forth. That's what I want you to understand, all right? Here is an example of a question. You may see this a conception. Which statement best explain the difference between a law and a theory? Unless you read the relevant section in the lab manual, not lab manual, but in the text, understand, make your own notes. I don't think you'll be in a position to answer the questions like there's someone we have on the PowerPoint slide. So here, explain the difference between a law and a theory. A law is a truth. A theory is merely a speculation. That sounds weird. We didn't talk about the truth in the law. A law summarizes a series of related observations, and a theory gives the underlying reason for them. See, a theory describes what nature does, and a law describes why nature does it. True. From what we went through, the correct answer is B. A law summarizes a series of related observations, and a theory gives the underlying reason for that. Without a proper understanding of the law and a theory, which I expect you to make your own notes, I don't think you're in a position to answer such a question. So go back and summarize those terms associated with the scientific method, all right? Go back, make your own notes, and understand what those terms are. Let's moving forward to section 1.3, classification of matter. Remember, matter can be classified as solid, all right? And by the way, you should be able to also have those terms. Let's say solid here, I'm going to be using S for solid, and then there is liquid, and then there is gas right here. These are the three states of matter, and virtually most matter will exist in any of those states if you change the temperature. If you change the temperature, matter can change its state from, let's say, solid to liquid. If it is H2O, it can change from solid, ice, to liquid, H2O. Remember, it's also H2O in solid state, H2O in liquid state. If it changes to vapor or steam, it's still H2O. I want you to master these physical changes. I know we will see later on, but matter can exist in these three states. If we change the state from here to there, we're gonna come back to that. There is solid, so that we get it right away. I know we're gonna come back to this later. These are the 6 changes associated with that if we change the temperature. Solid, liquid, and gas. We call these freezing. I know you know this. There is melting. There is here condensation. There is vaporization. And then there is a change of state from solid to gas without going through the liquid state. We call this sublimation. Giving you heads up on where we are going. And this is a deposition. Change of state from gas to solid without going through the liquid state. The point here is the 3 states, solid, liquid, and gas, which I want you to be able to classify matter. All right, I defined earlier on at the beginning of the lecture what matter is. Matter is anything that occupies space and has mass. Occupies spaces means it has volume. For example, your text, all right, your chair, even your body are all composed of matter. We classify matter according to state. When we say state, it's either solid state, liquid state, or what? Or gaseous state. And this composition, basic component that makes it up. If we change the temperature, all right, changing the temperature, matter can change its state from solid, for example, solid ice. If you raise the temperature above 0 degrees Celsius, it will melt, melting, freezing, changing the temperature below 0 degrees Celsius and so forth. You need to know, you should be able to reproduce a diagram similar to what you see on my whiteboard. It will help you in mastering and committing to the memory, the 6 terms associated with change of state. The 6, 1, 2, 3, 4, 5, 6. These are the 6 changes of state. All right, structure determines the properties of what? Properties of atoms. This just representing, I guess, solid matter, liquid matter, and gaseous matter. If you look at the how atoms are packed, in solids, they are rigid. They are rigid, they are in fixed position. In liquid, even though atoms are in contact, but they are able to roll over one another. I don't know if you are able to see liquidator. I know you are familiar with this. The liquidator water molecule are able to uh, rotate or roll over one another. Excuse me. So for gases, you see they are not in contact. They have large intermolecular or intermolecular spaces. This explains why gases are compressible. So if you are given a diagram or 3 diagrams, you should be able to identify which one represents solid, which one represents liquid or gas, depending on intermolecular spaces. Solid matter. Let's start from here. Solid. I will, in order to just briefly differentiate the properties for those, I'll say here is solid, liquid, and gas. Solid, liquid, and gas, like that. And then I'm gonna have here volume and shape. This is just a summary of properties of solid, liquid, and gas. So that this one, they have a fixed volume. They have their own fixed shape. I have my calculator. It has a regular shape. This is a calculator I'm holding. It's a solid. It has a fixed shape. That is what is meant by the check mark I have on my whiteboard here. It has a fixed shape and a fixed volume. It will never change. But for liquid, they have a fixed volume, but they don't have their own fixed shape. It can take the shape of any container. For example, the water I do have here in my container, if I put it in a rectangular container, it will assume the shape of that container. That's what is meant by the X. And here, gases, they don't have their own shape, they don't have their own volume. They occupy the volume of a container. If we have a light container, they spread out. They don't have their own shape as well. They assume the shape of the container. What I have on my whiteboard is just a summary of the properties of solid, liquid, and gases, which you need to know. All right. They do not move around past each other. They have just in fixed position. Ice cream or ice solid, aluminum, diamond, for example, they have fixed volume and rigid shape. Underline the word volume. fixed and rigid shape. So that's what is meant by the check mark here. These are just few examples of solids. Solid matter may be crystalline, may be amorphous. The slide here is just to illustrate what is meant by amorphous, and crystalline means it has regular shape. This one, it has irregular shape. That's what is meant by amorphous. Do not have any long range order. So for amorphous, we don't even see it here, but for diamond, all right, there is a crystalline regular pattern, but for class, it's amorphous. Liquid matter have fixed volume. Look at this, fixed volume, but not fixed shape. So that's why I have a check mark here. They have fixed volume and no shape. If we go look at the gaseous state or gaseous matter, they don't have their own one. They don't have their own shape. They don't have their own volume. They assume the volume of the container. They have large intermolecular forces, and this diagram here represent compressibility of gases. They are compressible because of large intermolecular spaces. So that's just in brief summary of classification of matter, solid, liquid, and gas. You should know their properties as well. Make your own notes on that. Moving forward, matter can also be classified by its component. All right, let me blow up this so that we can see the flow chart of classification of matter. Matter can further be classified as pure substances or all mixtures. All right, and pure substances, they have well-defined, all right, their composition is known, whereas for mixtures, they have variable composition. Example is sand and H2. If you mix, it has variable composition. Now, for pure substances, they have definite. That means it's well defined. For example, sugar, that carbon and oxygen and hydrogen, sodium chloride, sodium, NaCl. Those are pure substances. Now, elements, these are the elements on the periodic table. The author here is just using helium as an example. But if you can think of all the elements on the periodic table, okay, it falls on this side of the flow chart. And then compounds, these are compounds are made up of elements, all right, which combine in a specific ratio, such as H2O here is made up of one oxygen and two hydrogens. For wet sand, there is water, there is sand, right? There you see water molecule, you see the sand, where T is homogeneous. Homo means more than one. Let me just close this C, and if I can further illustrate that we have matter here. And then mixture. Homogeneous, hetero. And then here is pure substances and elements. You see here, compounds, and here compounds and the elements. I'll start by saying or defining what homogeneous, this means when you mix two substances, you end up with only one phase. It's only one phase. For example, dissolving table salt and sodium chloride in H2O, you'll only see liquid. You will not see two layers. That is what I meant by phase here. So if I have Na sodium chloride plus H2O, it will form an homogeneous. Alcohol and water homogeneous. Compared to hetero, you have to see this homo for one. Heterogeneous. Heterogeneous contains two or more phases. Two or more phases. What I mean by phases are layers, e.g. oil plus H2O. Oil plus H2O, right? Sand plus H2O. You should have a sense of what heterogeneous means. You can have more than two layers, or you can have two layers. It's not that you will be given a list of all homogeneous compounds or a list of all heterogeneous compounds. All you have to do is understand what heterogeneous mixture means, what homogeneous mixture means, so that when you are given a specific mixture, you should be able to classify it as heterogeneous or homogeneous. I was just looking at this flow on this side of the flow chart. If I look at mine, it's right here. You should be able to give example of heterogeneous, homogeneous. If I were you, I will make my road notes, try to understand the difference between those two terms. Let's look at this right here. Elements and compounds. Elements and compounds. Compounds right here. But before even we go there, mixtures. Mixtures can be separated into pure substances by physical means, by physical means. One, e.g., filtration. We will talk about this. You can separate a mixture into pure substances by physical means. Filtration, we will talk about this. Filtration, distillation. All right. Just to give you a few evaporation, you're familiar with evaporation. These are physical means by which mixtures can be separated. If you are taking a lab this semester, or if you took it before at UNF, there is an experiment on separation of component of a mixture. You will have hands-on experience on filtration. You're gonna talk about the vacuum filtration. I don't want to get in details into that. And even evaporation. Those are techniques you need to understand what they are. I'll share YouTube videos on these techniques so that you understand it will be handy in the lab. So these are physical means by which mixtures can be separated into pure substances. Now coming to compounds, here compounds. When two or more they form compound, right? This one form compounds. Two or more elements can form compound, e.g. H2O. This is a compound. NaCl. This is a compound. You can only separate compounds into pure elements, all right, by chemical means, e.g. Electrolysis of H2O will give us pure hydrogen, and oxygen is only by chemical means that you can separate compounds into pure elements. Just to give you flowchart on this, it's not the way you look at the PowerPoint slide on classification of matter. This is just a summary. There is more that goes in there. You may be given a mixture and you are asked to identify whether it is heterogeneous, whether it is homogeneous mixture. You need to know those homogeneous mixture, heterogeneous mixture. Is by understanding the nature of that. Does it have variables? We'll talk about that down the line. So here is the first division in classification of matter between pure substances and mixture. You see, I have the mixture here and pure substances. Now, pure substances are made up of only one component, and its composition is invariant. That means it does not vary. But for mixtures, they vary. We're talking about the pure substances versus the mixtures. A mixture, by contrast, is a substance composed of two or more components in proportion that can vary. Underline the word vary here from sample to sample. It's not the same. Okay? If you make a mixture of sand and sugar, you may not have a uniform mixture. You may have high concentration of one pure substance on one region. The other region may have substance with high concentration of one component. Now, there are two types of pure. Now, on this side of the flowchart, classification of matter on this side, this is out by the way. On this side, elements and compounds. Elements cannot be broken down into simpler substances. Elements include, on the periodic table, you see here, elements. These are just building blocks. We can call this building of matter, building block of matter, e.g., hydrogen, helium, sodium, oxygen, sulfur, anything you can think of. I'll say periodic what? Periodic table. I know we have not covered this, and it's the first time you're seeing me talking about periodic table. But you know what periodic table is? Anything on the periodic table fall under elements on the flowchart. So here I'll say periodic table here. See periodic table. That's what consists of pure elements. Compounds, on the other side, compounds can be separated into elements using by chemical means, So substance that cannot be chemical, talk about chemical separation of compound, but elements, you cannot chemically break it down into simpler substance. They are the basic building blocks of matter. I know I wrote it here, building blocks of matter. That's what matter is. And what we mean by that, we can build H2O from oxygen and two hydrogen atoms. Composed of a single type of atom such as helium. All right, helium, by the way, you should be able to write the chemical symbols. Just to give you a heads up, I know you may have covered, I'm using this term, even though we have not started or looked at the periodic table. Helium, chemical symbol for helium, He. Carbon is a substance composed of two or more elements in a fixed defined composition. What this means is you will never see, let's say, for example, water molecule written like this. Let's say you divide by two. It has a defined proportion. H2O will always be H2O. Sodium chloride will always be sodium chloride. Sodium carbonate will always be sodium carbonate, and so forth. There. All right, just to give you what this means, that compounds are composed of two or more elements in a fixed, underline the word, definite proportion. It means it will never change. The ratio will always be the same. Most elements are chemically reactive. That means they combine with one another to form compounds, such as water. All right, it's made up of oxygen and hydrogen. Mixtures can be heterogeneous. I have explained that before. Hetero means more than one phase. All right. Hetero means more than one phase. Heterogeneous mixture is one with a composition varying from one region to another. That means varying phases can be 2, 3, and so forth. Example is sand and salt mixture. They don't have the same proportion, no. Compared to homogeneous mixture, homogeneous is a mixture made up of multiple substances, but they appear to be pure substances. Look at homogeneous mixture, e.g. air, all right? Air, in air we have CO2, we have H2O in gaseous form, there is carbon dioxide, there is nitrogen, maybe even carbon dioxide. This makes up air. It's an homogeneous mixture. Alloy, know what an alloy is? It's a mixture of two metals, but they do not form chemical bond. It's just blending into one another. Alloy, for example, brass, all right? Steel, for example, those are alloys. I can say steel, for example, has a uniform mixture. We call it hetero or homogeneous mixture. Giving you a few examples of what homogeneous mixture is. All proportion, they have the same composition. Even sodium chloride plus H2O, sodium chloride plus H2O, assuming it's not super saturated, all right, to an extent that sodium chloride do not dissolve anymore, but sodium chloride in H2O will give us or will give you homogeneous mixture. Conceptual question, this is you know, something which requires you to think. In these three images you see here below, A blue circle represents an atom of one type of element, and a red square represents an atom of a second type of element, which image is a pure substance. If I look at this is a mixture. They don't form a chemical compound. Even likewise for this, but this one, there is a chemical bond between blue circle and a red square, which means A is a pure substance. The correct answer is A. It's a conceptual question for understanding classification of matter as solid, not solid, but heterogeneous, homogeneous, or compound and elements. These are just two elements. These are just two elements. Oh, I had mentioned about the separation of mixtures, which I think you need to go back and make notes on this. Some of them you are familiar with. Mixtures can be separated based on the component, physical or chemical properties of those will determine which method you are going to use to separate the two. Various techniques that expose the different in physical and chemical properties of individual substance in a mixture can be used to separate. Of what I want you to understand is the technique mentioned here, for example, decanting. What does decanting mean? You will use this, or you may have used this in the past. Decanting is pouring off, carefully pouring off. If this is a mixture, I can pour off what is the residue will settle down. The residue will settle down. You may see right now, and the liquid up, I can pour it off in such a way that maybe using a different one. If there is a mixture here, I will pour it off into a separate container, leaving the residue. Here in, if I have here, if you have we call this residue. That means the solid. What will settle down, and the liquid here, we call it supernatant. The proper term you'll see in the lab is supernatant. It's the liquid which remains. So I can pour off the liquid into a separate container, and what will remain at the bottom will be the solid residue. The technique of pouring off is called decanting, decantation. You need to know what that means. Now, distillation, all right? Distillation is a technique by which a mixture can be separated into pure substances by taking advantage of their boiling point. If two substances have different boiling point, you can use distillation. You'll see this in details, or you use in organic lab to separate mixtures. Alcohol, for example, ethanol boils at 78 degrees Celsius, water boils at 100 degrees Celsius. We can separate the two by using distillation method. And in this process, a mixture is heated to boil off the more volatile, easily vaporizable. In this technique, this is the distillation apparatus where there is the inlet to let in the cold water. And if this is the mixture, sometimes we have it in the heating mantle or some sort of heating device, so that this mixture, the most or a more volatile liquid will vaporize, it will travel as a steam. Once it gets here, it will condense and can be collected up down here as the mixture will just down here and then come down. This is either wire case or the mantle. Here is the mixture, sorry. Here is the mixture. Here is the cool water out, cool water in, so that the steam will come, will rise, it will condense on this condenser. We call this condenser. This is how distillation apparatus look like. You will use in organic if you're staying all the way to organic labs. There is the filtration, which is the pouring off or separating the component using a filter paper. There is vacuum filtration. See that in the lab manual. And in filtration, you separate the two, or you separate mixtures. One of them is insoluble solid. The liquid will go through the porous material, leaving behind the solid. This is called the filtrate. What will remain on the filter paper is the residue. This is just to guide the liquid in separation. You learn the technique of folding the filter paper. This is one of, I'm sure this is one of the technique you'll use in the separation of a component of a mixture. All right, moving on to section 1.4, physical change and chemical change. There are four terms which I want you to understand and draw the parallel. If need be, make your own notes on this. And these are, look at this. There is the physical and chemical what? Chemical change. And then see here is physical and chemical property like that. Physical or chemical property. So here we are talking about a change. You know, when we say change, if I say change the position, that means you move from here to here. In this section, we should be able to classify a change as chemical or physical. Here, the physical, how do you know a change is physical change? You need to ask yourself, one, did the chemical makeup change? If not, then the change is physical. Or rather, chemical does not change chemical composition. Or chemical makeup is not altered. That means we do not change that. We do not alter in that change. It remains the same. All the changes I mentioned earlier on consist or make up this, e.g., one, melting, freezing, vaporization, condensation, sublimation, deposition. Even I've seen here that is dissolving the solution. If you dissolve sugar in H2O does not mean that a chemical change has taken place, or dissolving sodium chloride table salt in H2O, you can get back your what? Your H2O. In fact, I should have said here reversible. Here, physical change is a reversible. That means you can reverse. All right. What I mean by reversible is in case, for example, I was just giving you example of dissolving H2O in dissolving sodium chloride in H2O, you can get back your sodium chloride by evaporation. All right, so it is reversible. This is physical change. In chemical change, here, chemical, if chemical makeup is altered, that means you change. It is altered. If a chemical makeup is changed, then you make a conclusion that that change is chemical. We can also say that irreversible. That means you cannot go back. Example is e.g. Rusting, burning, has to keep you digesting. Let's give you a few examples on chemical change. Now, a change that alter, you see, that means it changes only the state appearance, but not the composition is a physical change. Note of what I said about reversible, irreversible. I've given you a few there. Atoms, molecule that compose a substance do not change their identity. Yeah, so it does not change the chemical makeup for that. If it does, then chances are that is a chemical change. Here is a few, or you have just been given an illustration. When water boils, it changes its state from liquid to gas. Remember what I said earlier on when I was giving you I gave you the physical, but the states of matter, there were 6 changes of state, which I do have it here, by the way. 1, 2, 3, 4, 5, 6. All those fall under what? Under physical change. There is the dissolution, which was not in the flowchart, but here are the 6. Look at the 6 physical changes. Here on the PowerPoint slide is just capturing vaporization, which is change of state from liquid to gas. Liquid to gas. Now, chemical change, if a chemical makeup is altered, and then, all right, if a chemical makeup is altered, or if it is irreversible, then that change is considered as chemical change. So chemical changes are changes that alter the chemical composition of matter. Here is a nail undergoing rusting at the moment. Zooming in on this or on the surface of the nail, there is a combination of iron, we have it here, and liquid H2O. The process is reversible. I think I gave you that rusting, for example. chemical change. All right, rusting of iron. Please make note of all this. I think there is a few examples here on the physical changes. Dry ice. We don't change the chemical makeup of CO2. Physical change. Dry ice, just melt. This is solid to gas without going through the liquid state is sublimation. Right. So here a chemical composition unaltered in dissolving. Remember dissolution, dissolving sugar. This is dissolving sugar. You need to, dissolution is a physical change. Now, burning of propane. This is propane gas. We end up with different irreversible, different substances, irreversible processes, chemical change. These are just few. In the exam, you will see more or different types of changes, and I will expect you to classify a change as either physical or chemical. Do more practice on those. If need be, please let me know. Now, I'm done with the physical changes, chemical changes. There is now a property. What is a property? Before we look at the physical changes, there is the property. I want to say property. This is we can define this characteristic feature for describing, let's say, just matter. Characteristic feature you can use to define matter is a property. I have a green pen here. I don't know if you can see. Oh, you can see, like, I have a green pen. I'm using color, e.g. Color. If I say green apples, I'm using the appearance. It's characteristic feature used to describe matter is a property and can be either physical or chemical. Even state is a characteristic feature, e.g. solid, liquid, or gas. For there is water in my water bottle, is in liquid state. I'm using the state to describe what is in this bottle. It's liquid. All right, physical. Physical property, chemical property. What is the difference between the two? A physical property is a property that substance display without changing the composition, something you can measure. For example, boiling point, melting point. We can measure this without changing the chemical makeup. For example, water boils at 100 degrees Celsius. It does not mean when it starts changing its state from liquid to gas, we have altered. No, we can measure it. We can measure the temperature of of a substance, but that does not mean we are changing its composition. Or smell of gasoline, for example, does not mean you change. So the odor here, taste, color, appearance, melting, boiling point, and density are all physical properties. I'm talking about density, you know, this is concentration. We can talk about concentration of matter, all right? Density, we will talk about that in a few minutes. Now, chemical property on the other side describes the chemical reactivity of a substance. Gasoline is flammable, that means it can burn. Liquid H2O is non-flammable. How do I know? It's if I ignite H2O, it will not. that is its chemical property. It has to do with the chemical reactivity. Concentrated HCl is corrosive. That means it can eat, it can digest anything. It has to do with the chemical reactivity, and that is a chemical property. Flammability of gasoline, in contrast, it's a chemical property. Chemical properties include corrosiveness. I just mentioned that using HCl, acidity, toxicity, and so forth. Please understand or draw the parallel between physical property and chemical what property. Here is a learning check. If it was in face-to-face, probably we could use the eye clickers and see how we will respond. We have captured, understood physical, chemical properties, physical change, and chemical change. There we go. Is the following change physical or chemical? Plants make sugar from carbon dioxide and H2O. Can we reverse the process once the plant make sugar from CO2 and water? Is it reversible? I don't think so. Therefore, it is a chemical change. It's one way. If it is reversible, then it's physical change. In this case, the process is irreversible. Conceptual question, the diagram on the left, which is this one right here, represent liquid water molecule in a pan. Which one of the three diagrams, A, P, C, A, P, or C, best represent the water molecule after they have been vaporized by boiling? There is no way you will split the water molecule into separate components. So I'll say A is the correct, all right? A is the correct response for this question. Now, there are two types of properties apart from chemical, all right? We have looked at, you need to know this. Properties could be one, chemical, two, physical. And what we have on the screen here is intensive. So here is the intensive for extensive, extensive. What this means is intensive, independent. Look at what I've underlined, independent on the amount of substance. For example, density is an intensive property. Density of H2O will always be 1.00. Even if you have 10 ml, 5 gallons, 100 liters, the density will remain the same. Likewise for boiling point or melting point. The color, these are important in identifying the color, looking at that. Now, extensive properties depend on the amount. For example, even area, extensive. Extensive properties, these include area, for example, to volume. It depends on the amount, the area of, I can find the area of this paper. You see the paper I'm holding. I can find the area by measuring the length and the width, length and the width. And if I have a large piece of paper or small piece of paper, it depends on the dimension. Therefore, area and also likewise volume, they fall under the extensive property. So some properties which could be physical can also be uh, classified as intensive or extensive, intensive or extensive. Got to know that. When we say that lead is denser than metal, than the aluminum, we are talking about extensive or intensive. I think the word here, denser, is density, which is intensive. Underline the word dense, it comes from the word density, and density is an intensive property. Don't let other terms, the length of the question scare you. Just think through the problem and classify a property as either extensive or intensive. Lastly, now on part A of our lecture, this is the last part of our lecture in part A, energy. Energy is defined as, you should be able to define this energy, it's defined as the ability to do work, or energy is the capacity to do work. Energy is the capacity to do work or ability to do work. It can be the most important type of energy as far as you are concerned is, even though we have other types, let's say form of energy, even though we have other forms of energy, the most important is kinetic energy and potential energy. This stands for kinetic energy, and this is potential potential energy. The most important type of energy. You need to know kinetic energy, potential energy. And potential energy is simply energy in motion. We'll say this is energy in motion. This can be just stored energy or the energy stored by substances, energy by factor of position. Let's see, energy is a capacity to do work, and work is defined as the action of force acting on an distance. To understand the difference between the two, for example, when you push a box across a hole or across the floor, or you pedal your bicycle across the street, you have done work. You have done work. What I want to point out is you should be able to define potential energy, kinetic energy. Kinetic energy, abbreviated here as KE, is the energy associated with the motion of object. Here I say energy in motion. It's the same thing, all right? Potential energy is the energy associated with the position or composition. Position, what I mean by that is if I hold my calculator, it has some potential energy. If I release it, the potential energy will be converted to kinetic energy in motion as it drops. Once it hits the ground or the floor, the potential energy or the kinetic energy will be converted to thermal energy when to hit or make the molecules move around here. So potential energy can be also by composition. Gasoline, by virtue of its composition, has some energy stored in it. If you break the molecule, energy will be released and it can be converted into other forms of energy. Thermal energy is the energy associated with the temperature of an object. What is meant here is if you drop weight on top of a building, kinetic energy. Once it hits the floor, kinetic energy will be converted to thermal energy, which is the energy associated with the temperature of an object. Oh, these are the two fundamental types of energy you need to know. Kinetic energy, which can be calculated, and I expect you to do this. Kinetic energy is a half mv square. This is the equation for calculating the energy. Where m equals to mass in kg. So by now, at least you should be able to convert the mass, from grams to kilogram and so forth. If need be, you may be given the conversion factor so that you change the mass to kilogram. And then V stands for velocity. This is velocity or speed of an object. Should be in meters per second. Take note of the units. If the unit is given in other than meters per second, you need to convert that. It's because if we are looking with energy, 1 joule equals to kilogram, 1 kilogram. This is joules. This is the units or SI unit for energy, SI unit for energy. So remember to change the units of mass to kilogram, right? Remember 1 kg equals to 1,000 grams. You may need that. I don't know if you'll be given in the test. So let's see, here is an example on how to, or if you look at the joule here, this is the unit. If you here, see this joule is because of the units for energy. 1 kilogram per meter square, 1 kilogram times meter square by second square is what we call the joule, which is what? Which is the SI unit. Sometimes you may be given the problem on how to convert the units of energy from calories to calories. There's a difference between uppercase calories and lowercase calories. Uppercase calories, lowercase calories. All right, let's see an example on calculating the kinetic energy. Remember, you need to change the mass to kilogram and speed to meters per second. We haven't covered the dimensional analysis to change from 1 unit, but you should be able to do that from intro to chemistry. So we need to change these to kilogram. Where are you going to get the conversion factor? You'll be given in the problem or some of the conversion factors. I'm going to talk about the dimensional analysis end of chapter 1 so that you see what I mean by the conversion factor. Now, nevertheless, let's change the mass or convert in ounces to kg. Give it this, look, 1 ounce equals 28.3495 grams. And 1 kg equals 1,000 grams. So these are the conversion or equivalent statement. We need to convert this to kg so that when we set up this, it's going to be 5.13 ohms Ons will be at the bottom. We are looking for times 1,000 grams. It's 1,000 grams on it. It's gonna be 0.1454. This is now the mass in kg. Why do we have to change the kg? It's because of the equation for kinetic energy. Mass should be in kilogram. And lastly, we need to change the what? Speed from miles per hour to meters per hour. So here's 95.0 miles. How many in meters per second? Given this, or you may have to find out 1 mile equals 1.609 kg. And of course, 1 kilometer equals to 1,000 meters. And 1 hour seconds. So here are the conversion factors. We need to change this to meters per second. So if we plug in that, this will be 95.0 meters per miles. Oh, it's miles per hour times. We need to change to kilometers. 1.609. It's gonna be 42. This is meters per hour. It's gonna be. This is something you need to remember. This equivalent statement, you may need to find out if it's homework assignment. You have to use the text to look at the conversion. By end of chapter 1, you will have, or we will have covered the dimensional analysis. What I'm using right now is compound dimensional analysis, where I'm using more than one conversion factor to arrive at my answer. Note how I set up my equation so that this will go away, mile and mile will go away, hour and hour will go away, so this and that will go. This and this will go. And this is kilometer will go away per second. So that now, therefore, kinetic energy equals to a half into four, 5, 4, 3 kg times 4 this equals to 131 joules. This is 131 joules using the kinetic energy equation to find the energy over moving. So in all other calculation, make sure you get the correct conversion factor, set your equation, and you should be able to get the right answer. Other than that, that marks the end of part A of the lecture. I'll come back again for part B. All right, that marks the end of part A. I was just splitting it into two so that the lectures or the lecture recording doesn't take like 2 hours or 3 hours. See you shortly. Thank you.